Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Department of Physics, Central University of Haryana. Today we are going to discuss about a module, connection between state vectors and wave functions, under the paper Quantum Mechanics 1. So students, let us see what we are going to be learning in this module. Firstly, we'll get to know how to represent a wave function starting from state vectors. In this, we'll also see that basically the vectors in the normal coordinate representation become state vectors in the quantum mechanical formalism, and the wave functions of the quantum mechanical formalism are just the corresponding wave functions of the classical mechanical formalism or the normal coordinate system. Then we learn to express dynamical variables as matrix operators and write the matrix equation relating the wave functions as column vectors to the dynamical operator represented as a square matrix in a given representation, where the given representation could be either the coordinate representation or it could be the momentum representation. Then we'll get to know how to write the relations between state vectors and the wave functions in x space and in the momentum space. And finally, we'll learn that the wave functions in the x space and the p space are connected through unitary transformations, where the wave functions in the coordinate space can be represented in the momentum space through a Fourier transformation and vice versa. Then we'll deduce that while in the x representation the operator x is diagonal, the momentum operator p is the differential operator given by minus I h cross del by del x, where h cross is the equal to h by 2 pi and h is the Planck's constant. Similarly, in the momentum representation, the operator is diagonal, but the operator is given by minus I h cross del by del p, which means in the momentum representation, the operator p is diagonal, but the operator x or the coordinate operator is given by the equation or by the differential operator minus I h cross del by del p. Then finally, we'll know in general how to define unitary transformations and unitary operators and learn that the change of basis corresponds to a unitary transformations. So, in continuation of the last topic discussed in the preceding module, here our main objective would be to study representations of state vectors in a Hilbert space and learn how different kinds of wave functions for a given state, as for instance in configuration space and momentum space, etc., are simply the sets of components of the state vectors which may be regarded as different coordinate systems or bases in the state vector space. Then we shall also explore how Dirac's Ket and Bra notation greatly facilitates the interrelationship between different representations and demonstrate to express dynamical variables as matrix operators and write the matrix equations relating to the wave functions as column vectors. To the dynamical operator represented as a square matrix in a given representation. Another interesting aspect is to study using the quantum condition and deduce the explicit representation of the dynamical variables such as position and momentum operators in a given basis. Relation between state vector and wave function in X space. Now let us look at the applications of the representation theory of state vectors. So for discussing the applications of the representation theory, let us consider the Schrödinger representation where the operator A is equal to operator X in one dimension. Now, if the basis states are represented by the ket vector A of the operator A representation, then the position eigenstates are represented by the ket vector X, where the position operator X can be defined as position operator X acting on the ket vector X, that is the position vector X, is equal to the eigenvalue of X times the ket vector X for all X lying from minus infinity to plus infinity. That is, for a one-dimensional coordinate going from minus infinity to plus infinity. The result of the measurement of the position x of the particle can be any real number lying between minus infinity and plus infinity. The eigenvalues x as defined in the above equation, forming a continuum of the Hermitian operator x. Assuming that eigenstates are normalized, we have bra vector x ket vector x prime is equal to delta x minus x prime, which means that for the Hermitian operator x, the position eigenstates x are normalized, and if they represent different eigenstates, then the product goes to 0. Relation between state vector and wave function. The wave function of an arbitrary state ket vector psi or the state vector psi is given by bra vector x ket vector psi, which is the Schrödinger wave function psi x. That is, the Schrödinger wave function psi x is equivalent to or is given as bra vector x ket vector psi. The norm of the arbitrary state psi is expressed as bra vector psi ket vector psi is equal to integral over dx bra vector psi ket vector x bra vector x ket vector psi is equal to integral over dx square of the modulus of the wave function psi x, where we see that the state vector x are normalized. Thus, the norm of psi is given by the integration over dx of the square of the modulus of the wave function psi x. Note that in the case of continuum, the summation over projection operator I is replaced by integration. That means that in case of continuum, where we do not have any discrete values, or the operators and the observables or the coordinates are not taking discrete values but are taking continuous values, there the projection operator I is defined as integral over dx ket vector x bra vector x, the scalar product of two state vectors. So now if we have two state vectors defined by state vector psi a and state vector psi b, then the scalar product of these two state vectors is given as bra vector psi a ket vector psi b, which is the scalar product, is equal to integration over dx prime bra vector psi a ket vector x prime bra vector x prime ket vector x bra vector x ket vector psi b, and this is equal to integration over dx prime psi a x prime star delta x minus x prime psi b x, where psi a x prime star is the complex conjugate of the wave function psi a x prime, and the delta operator states that if x and x prime are two different coordinates, then the delta operator will go to 0, and if they are same, then the delta operator goes to unity, and thus the scalar product of the two state vectors bra vector psi a ket vector psi b is given as integration over dx psi a x star psi b x, where psi a x star is the complex conjugate of the wave function psi a x. And here we have used the completeness relation in order to reach this result. And we also define what is meant by orthonormality. So, orthonormality means that if we take the scalar product of the two state vectors, bra vector psi a ket vector psi b is equal to integration over dx psi a x star psi b, this is equal to 0 for all state vectors psi a and psi b where a is not equal to b. Wave function in x representation. Here we have obtained the coordinate representation of the wave function for the position operator x. In this representation, the operator is diagonal, that is, bra vector x operator x ket vector x prime is equal to x prime delta x minus x prime. So what this means is that for all matrix elements other than the diagonal elements, we have that the matrix elements are all 0, and only where the matrix elements are the diagonal elements, they will have some values. As a result, operator x acting on the state vector psi gives bra vector x operator x state vector psi is equal to integration over dx prime bra vector x operator x ket vector x prime bra vector x prime ket state vector psi is equal to integration over dx prime x prime delta x minus x prime psi x prime, and this is equal to x psi x. To find the action of the operator p on the ket vector psi, that is the state vector psi, in the x representation, we shall make use of the postulate of quantum condition on the commutation relation. Commutation relation of operator x and operator p is equal to IH cross, where H cross is equal to H by 2 pi and H is the Planck's constant. And we find that using this condition, we have bra vector x, operator px minus operator p, operator x, that is the commutation relation of operator x and p, get vector x prime, and this is given as, or this is equal to IH cross bra vector x ket vector x prime is equal to IH cross delta x minus x prime, where we have used the above identity for solving or simplifying this equation. The left hand side can be simplified by using the property operator x acting on ket vector x prime is equal to eigenvalue x prime ket vector x prime and bra vector x operator x is equal to x bra vector x, which gives x minus x prime bra vector x operator p ket vector x prime is equal to IH cross delta x minus x prime. Action of operator p on the wave function psi x. So continuing from the previous equation, we can rewrite that equation as bra vector x operator p ket vector x prime is equal to IH cross delta x minus x prime upon x minus x prime is equal to IH cross del by del x prime of delta x minus x prime, where in the last step we have used the identity x into del by del x of delta x is equal to minus delta x. However, if you see in the above equation where we have used this identity, the negative sign is not occurring. The reason for that is that in the above equation we have used the partial differentiation of the del x minus x prime with respect to x prime and not x, and that's why the negative sign does not occur. To find the relation operator p acting on state vector psi, we write bra vector x operator p ket vector psi is equal to integration over dx prime bra vector x operator p ket vector x prime bra vector x prime ket vector psi is equal to IH cross integration over dx prime within brackets del by del x prime delta x minus x prime psi x prime. Now, in order to solve this integration, we use the method of integration by parts, and using the integration by parts, we get the relation bra vector x operator p ket vector psi is equal to minus IH cross del psi x by del x. In this manner, we show that the operator p acts as a differential operator minus IH cross del by del x, or in this manner we have actually defined the momentum operator p in one dimension. Generalizing this result to three dimensions, that is, if we want to now define our momentum operator or the operator p in three dimensions, we can write this as that instead of our one-dimensional coordinate x operator, we replace the one-dimensional operator x by the three-dimensional operator r or the vector r and the corresponding one-dimensional operator P, a momentum operator P, is represented by the momentum operator P vector, and this momentum operator P vector is equal to minus I h cross del vector, where del vector is actually the del operator, which is given by I cap del by del x plus j cap del by del y plus k cap del by del z, where I cap, j cap and k cap are the unit vectors along the x, y and z coordinates or axis respectively. Wave function in momentum space. It is interesting to see how the operators x and p act in the momentum representation. Since up till now we have been discussing the operators x, that is the coordinate or the position operator, and the momentum operator in the coordinate or the space representation. So now if we want to study these operators in the momentum representation, we can first define the basis states ket vector p as operator p acting on ket vector p is equal to p times ket vector p, where p are the eigenstates for the basis states ket vector p of the operator p, giving the continuum of eigenvalues p of a Hermitian operator p. If the states are normalized, then we have bra vector p ket vector p prime is equal to delta p minus p prime, and the wave function of any arbitrary state ket vector phi is given by bra vector p ket vector phi, which is the Schrodinger wave function phi p in momentum space. And this wave function phi p in momentum space is given as phi p is equivalent to bra vector p ket vector phi. And the norm of this wave function in momentum space, or the state psi, state phi, can be expressed as the norm of phi, that is bra vector phi ket vector phi is equal to integration over dp bra vector phi ket vector p bra vector p ket vector phi is equal to integration over dp square of the modulus of the wave function phi p in momentum representation. The operator p is diagonal, which means that bra vector p operator p ket vector p prime is equal to p prime delta p minus p prime. That is, that all the matrix elements of the matrix corresponding to the operator p have all off diagonal elements going to 0, and the only values that the operator p will have in terms of the eigenvalues are on the diagonal elements only. Operators x and p in momentum space. As a result, the wave function of operator p acting on state vector phi is given by bra vector p operator p ket vector phi is equal to integration over dp prime bra vector p operator p ket vector p prime bra vector p prime ket vector phi. This is equal to integration over dp prime p prime delta p minus p prime phi p prime, and this is equal to p phi p. Here, in trying to simplify, or in order to simplify the above equations to reach the final result, we have used the identity of the unitary matrix, that is, operator I is equal to integration over dp ket vector p bra vector p. Now, if we want to find out the wave function of operator x acting on state vector phi, we shall make use of the postulate of quantum condition on the commutation relation between the operator x and the operator p, which is commutation relation of operator x, operator p is equal to IH cross, as was defined earlier. Considering the matrix element of this relation between the states p and p prime, we have bra vector p, operator x, ket vector p prime is equal to IH cross delta p minus p prime minus p upon p prime minus p is equal to minus IH cross del by del p prime delta p prime minus p. Here we have used the identity that was defined earlier, which was p del by del p delta p is equal to minus delta p. Next, we can write the relation between states p and p prime as, or rather now the relation between states p and the wave function phi as bra vector p operator x ket vector phi is equal to integration over dp prime bra vector p operator x ket vector p prime bra vector p prime operator phi, and this is equal to minus IH cross integration over dp prime within brackets del by del p prime delta p minus p prime phi p prime, where we have used the commutation relation between the operators x and p in the above equation to get this result. Now let us study the relation between momentum and space wave functions. So using the same procedure as we had done previously of doing the integration by parts that was used in the earlier equation, we get bra vector p operator x ket vector phi is equal to IH cross del by del p phi as a function of p. Thus, in the p or the momentum representation, while the operator p is diagonal, the operator x acts as a differential operator IH cross del by del p, acting on the momentum space wave function. It is important to observe that these representations are derived based on the quantum postulate of commutation relation. To obtain the relation between two wave functions, we note operator x acting on wave function phi p is equal to operator x bra vector p ket vector phi is equal to integration over dx bra vector p ket vector x operator x bra vector x ket vector phi, and this is equal to integration over dx x times bra vector p ket vector x phi x. Momentum and space wave functions. We can also see that operator x acting on wave function phi p is equal to IH cross del by del p phi is equal to IH cross integration over dx del by del p bra vector p ket vector x bra vector x ket vector phi, and this is equal to IH cross integration over dx phi x del by del p bra vector p ket vector x. Now on comparing this equation with the previous equation, we find that d by dp bra vector p ket vector x is equal to minus I by h cross x times bra vector p ket vector x. Now, if we want to integrate this equation, we can call bra vector p ket vector x as equivalent to some xi, then d xi by xi is equal to minus I by h cross x dp. On integration, we have log of xi is equal to minus I by h cross xp plus c, where c is the constant of integration, or xi is equal to c times exponential to the power minus I by h cross xp. Therefore, bra vector p ket vector x is equal to c exponential times minus I by h cross xp, and substituting this result back in the above equation, we get, or we can write the equation for the wave function phi p as phi p is equal to integration over dx bra vector p ket vector x bra vector x ket vector phi is equal to c times integration over dx phi x exponential to the power minus I by h cross xp. Relation between momentum and space wave functions. The wave function in momentum space, as defined above, is the Fourier transform of the wave function in coordinate representation. One can, in a similar way, show that phi x, that is the wave function in coordinate representation, is equal to c star integration over dp phi p exponential to the power I by h cross xp, where c star is the complex conjugate of the constant of integration c. Here, the constant c is independent of both x and p and can be determined using normalization condition. Integration over dx with limits going from minus infinity to plus infinity, square of the modulus of the wave function phi x is equal to 1. Assuming the constant c to be real, we get c is equal to c star is equal to 1 upon under root 2 pi h cross. So we can write the wave function in the momentum representation as phi p is equal to integration over dx bra vector p ket vector x bra vector x ket vector phi is equal to 1 upon 2 pi h cross integration over dx phi x exponential to the power minus I by h cross xp. So here phi p is the wave function as is being represented in the coordinate space, and similarly we can also have this wave function as a function of the coordinate x being represented in the momentum space, and this is given by phi x is equal to 1 upon 2 pi h cross under the root, that is 1 upon under the root 2 pi h cross integration over dp phi p exponential to the power I by h cross xp. So in this manner we can see that if we look at the wave function in momentum space, it is simply the Fourier transform of the wave function in coordinates representation and vice versa. Unitary transformations. Thus, starting from the orthonormal set of bases in the x and p representations, that is in the coordinate and momentum representations, and using the quantum condition, we show that the wave functions in momentum and the coordinate space are related by the Fourier transform of each other. Or in other words, the wave function in momentum space can be represented as the Fourier transform of the wave function in coordinate space and vice versa. This is an example of a unitary transformation. That means a transformation in going from one space to another space through a Fourier transform. As a unitary operator is defined through the equation operator S dagger operator S is equal to I is equal to operator S dagger, where I is the unitary operator or the unitary matrix. In case the operator A is Hermitian, that is, operator A dagger is equal to operator A, that is, the operator A is equal to its adjoint, and we can define, or we have a parameter alpha which is a real number, then the expression exponential to the power I alpha operator A is unitary, and this is because exponential I alpha operator A whole dagger is equal to exponential I alpha operator A dagger, and this is equal to exponential I alpha operator A to the power minus whole to the power minus 1, or inverse, whole inverse, and this is equal to exponential minus I alpha operator A. So in this manner, through these equations, we can see that the expression exponential I alpha A is unitary. So students, now let us summarize what we have learned in this module. Firstly, we learned how to write the relations between state vectors and the wave functions in x space and in the momentum space, and show that they are connected through unitary transformations. And basically what we saw was that a representation in the x space can be represented in the momentum space through a Fourier transformation, and similarly a representation in the momentum space can be represented in the x space again through a Fourier transformation. Then we learned how to deduce that while in the x representation the operator x is diagonal, the momentum operator P is the differential operator given by minus I h cross del by del x. Similarly, in the momentum representation, the operator P, that is the momentum operator, is diagonal, but the operator x, that is the position operator, is given by the differential operator I h cross del by del p. And then we finally learned how in general we can define unitary transformations and unitary operators. And we also learned that the change of the basis corresponds to a unitary transformations, which means we actually learned how we can transform our state vectors from one basis set to another basis set using unitary transformations. Thank you.